Welcome all of you guys. I'm really excited to be here at FluentConf to be able to guide you through the challenges of scaling up a Node.js API. And in this talk, we'll not only deal with theoretical stuff, we'll also try to get our hands dirty by doing some practical things like profiling stuff and running tests and also looking at actual live code. And by the end of this talk, you'll be having enough knowledge and enough information to be able to know the ways around how to create a scalable, highly available, resilient, and responsive Node.js application, hopefully. But before I dive into the talk, let me formally introduce myself. My name is Volkan, and I have been writing JavaScript since 2003, so that's kind of a long time. And I haven't been bored about writing JavaScript. Right? JavaScript is really cool if you ask, how it worked out that way. And currently, I'm a technical lead at Cisco. We are at Cisco in our department creating APIs around our cloud streaming infrastructures. And before Cisco, I have been to a lot of places. And no matter what I did and no matter where I have been, my passion for JavaScript and performance and optimization has always remained. And you can follow me on GitHub and tweet me at Twitter and stuff like that. And by the way, you can download the source code and slides accompanying this talk at this website. And just a quick reminder, the slides that I have provided online is the audience copy. By audience copy, I mean it has much more material that you can dig into. This talk has around 80 slides or so, and the audience copy has a double that amount. So if you want to dive into some concepts that I won't have time to cover in the talk, I suggest you to go and download the slides or get the slide deck online as well. So our agenda will be basically twofold. In certain parts of our talk, we'll be discussing theory and trying to discuss best practices and patterns and practices about how we can scale our Node.js API. And in other parts, we'll be looking at actual source code, and we'll be doing some profiling and benchmarking and stuff like that. And during that talk, we'll also we'll first look into Node's strengths and weaknesses and see what Node.js is good for and what Node.js is not so good for. And then we'll learn to tweak our operating system to have a highly concurrent, resilient application structure, basically. And after that, we'll discuss the relationship between throughput, concurrency, and latency. And while we are doing all this, we'll be trying to scale up a kind of real-life application that does some natural language processing or natural language programming. So it could be fun. So it's not just a hello world application. It may have some real-life implications to it. So it will be more, like a real-life scenario in our case. So designing an API from end to end is not easy. So sometimes you think that if I write a Express application and if I put a bunch of RESTful API endpoints to it, it would be good enough. But to be able to make the API work properly end to end, you'll have to put a lot of components in the structure, and you'll have to make them play well and orchestrate well together to make the end-to-end communication with the service and the clients happen properly. And what you see in this picture is actually just the tip of the iceberg. There's a lot of other things like infrastructure automation, reactiveness to changes, auto-scaling, and security and stuff like that. And obviously, we won't have time to deal with all of these in this tutorial. So our main focus will be around this tiny orange box, which is our API service. And we'll start with a single monolithic application, and we'll treat it as a black box and try to analyze its performance characteristics, basically. And JavaScript will be our language of choice, of course. And when it comes to JavaScript, you'll have to know the powerful parts of it to realize the usefulness of it. And if you are coming from a different background, like, say, C# or Java, chances are that you have tried before to impose a lot of object-oriented patterns and practices on top of a JavaScript framework, which creates something like a Frankenstein, basically. And JavaScript, although you can write object-oriented way or object-oriented JavaScript, JavaScript has much powerful constructs that make your life much easier. For instance, you can take function, the function construct, for example. Function is as you know, the building block in JavaScript. And the good thing about the function is function doesn't have to be attached to something. It is a first-class citizen in JavaScript. Therefore, it doesn't have to be owned by an object. A function can accept a function, and a function in the same time return another function as a return value. And when we return a function, we kind of create an enclosed execution scope around that function, which is like all the environment frozen in time, which is called closures. And the concept of closures, when you think in a functional programming way, is just like using monads. So when you think in retrospect and think how you can write functional JavaScript, then you can realize that the functional nature of the language is really powerful and really unique to itself. And actually, it's not just the functionality or the functional nature of the language. When you are designing an API, say most of the time you'll be consuming a big blob of JSON from an external service, and then you'll be splitting that JSON into smaller JSONs and changing some piece of the smaller JSONs, like adding a bunch of fields, renaming certain fields, so that reduced JSON can make sense to the client that is going to consume it. And this is not in any way different than consuming an immutable stream of information and then mapping, reducing, and translating it to different yet immutable streams of other sorts of informations. And the thing that I have described is nothing but functional programming indeed. So the place that I'm trying to get at is the more you embrace the functional nature of JavaScript, the better of a programmer, an API programmer you will be in general, and the better a Node.js programmer you'll be in particular. So show love to functions, basically. And while we are designing an API, we'll also need to know the strengths and weaknesses of our framework so that we can use our tools wisely. And when it comes to Node.js, Node.js is an excellent networking library. And it's an excellent networking library wrapped around libUI, and libUI is a great I/O library. Therefore, Node.js is not surprisingly a perfect fit for real-time applications, I/O-heavy applications, and RESTful API-driven. I hate to say micro, but people call it microservices, so RESTful services, so to speak. And any kind of things that deals with streams is also a good fit for Node.js. So what Node.js is not so good for is basically doing CPU-bound work. The reason for it is Node.js is extremely sensitive to blocking I/O. So if you are consuming CPU too much, chances are that you are also blocking the main execution thread, which the event loop resides on it. So CPU-bound applications is not so good for Node.js. And also serving static files can be done by using much better tools like a content delivery network or like using Varnish, or even if you use Nginx to deliver your static files, it's better than Node. And also creating a monolithic application structure is quite against the Node.js philosophy, because as you know, Node.js, writing a Node application means that you are creating modules. And module by its definition is modular. An ideal module has to do one thing and one thing well, and that's the Linux philosophy. Therefore, most of the time when you start creating a Node.js application API infrastructure, you end up with a bunch of modules here and there and everywhere, and they are loosely coupled with some kind of a message bus, which is in and of itself another mess to deal with, but that's the way it is, basically. And also, Node.js is not a solution or a hammer for any kind of nail. And there are other tools and other frameworks that you can use for different sets of solutions than Node.js. Therefore, you should do your research well on what to use and what not to use. For instance, terminating SSL and compressing gzip files, compressing files as a gzip stream is more CPU intensive and therefore is not a good fit for Node.js. And we discussed the static asset part. And for load balancing, I strongly suggest you use a load balancer as a service. However, even if you use a software-based load balancer, it's much better than trying to write your own load balancer logic in Node.js. And we'll see an example of how we can do load balancer in Node. It's not hard, and there are sometimes reasons to do it so, but most of the time you'll be better off by using a load balancer as a service, so to speak. And the first thing that you'll need to do to make your system scalable, or to make your system react to a high level of concurrency, is to tweak it at the operating system level. And in this tutorial, we'll be discussing a Debian system. It's a Ubuntu box that we tried to install. And other Linuxes may have different ways of configuring them, so do your research accordingly. And I don't know what they do in the Windows land to configure the system at the system level, so to speak. And I don't know if people are using Windows on production to run a Linux service. With the Chakra engine, things are a little changing, but 90% of the time it's a Linux box, and probably it's either Ubuntu, Debian, or something like CentOS that your production node instances are running. And the first thing that you'll hit when it comes to the scalability limitations is the number of open file handlers on your system, which means when a server makes a request to your Node.js application, then the Linux box will keep a file handle open on the Linux server as long as the connection remains open. And Linux has an upper limit on the number of maximum file handles that it can carry on, and therefore to be able to accept a lot of thousands of concurrent connections, you will need to increase this open file handle limits to a couple of tens of thousands to be on the safe side. And also, you might want to use ulimit to set up your Node.js processes number of file handlers that it uses, so that it can handle adequate number of file handlers, and it is not blocked by the operating system's limitation on that. And if you don't do that, the typical error you get is this one, this EM file, too many open files. And when you see this, it means that you need to increase those limits, basically. And similarly, if you are using a load balancer as a reverse proxy to your Node.js server, and which is not uncommon if you are doing a production Node-based Node.js setup, basically, you'll also need to increase this number of worker connection limits. And this is an Nginx example. HA proxy has similar configuration as well. But the gist is you'll have to update your load balancer configuration to make it work for a highly concurrent connection load, basically. And additionally, if your service is getting too many concurrent connections too fast, like a big burst of connection that comes to your server, that might happen if if your API gets popular on Reddit and all the Redditors are flashing you like a DOS attack, which is a good thing, but it's also a pain in the where. So the way to fix it is to increase your maximum socket connections to a couple of thousands, and the default number is 128, which is the number of connections that your system can keep in the backlog before releasing them to the processes. But there's one caveat to this. If you increase this number too high, then you'll also introduce latency to your system. So there's always a balance in between, whether you prefer a connection rejection error from the server, or whether you want to wait your clients to wait a little longer to reach your API, basically. And there are even more tweaks that you can do. However, the things that we have seen so far are more than necessary or more than adequate to configure our server, configure our operating system to work on a highly scalable scenario. And if you want to dive deep in there, you can go and visit the links that has been provided in the bottom of this slide. But just a reminder, since you are tweaking the operating system in a lower level, you should be extra careful in, first of all, backing up your configuration files. That is the most common mistakes that you might do. You change the configuration and forget to back it up, and then your system goes into an unstable state, and you'll have maintenance nightmares that you haven't seen in your dreams, maybe. So that's one thing. Know your stuff, read the freaking manual, and then act accordingly. Actually, read the manual a couple of times. And enough of the theory, I guess. So we'll get our hands a little dirtier. We'll start with a really simple setup. We have a Hello World application that has been written in a API framework that some of us know. It's RESTify. The other is a simple, plain old, bare bones HTTP implementation of a Hello World application. And the other is a TCP socket application. So both of these just give you a Hello World response when you request a response from them. So, and we'll do an Apache benchmarking to test the performance of this. And this code piece is sending 10,000 concurrent requests, 10,000 requests at the level of 100, at the level of 100 for the concurrency. So we're sending at most 100 concurrent requests at each time with a total of 1,000 requests. And we'll see how our application responds to it. Oh, my desktops have swapped. I love it. So let's see where my terminal is. Okay, so let's zoom it a little. I'll just go to my, wow, this is smaller than I thought. Flow and let's try. Do I do displays and do this one maybe? Wow, it's better. Thank you. Oh, okay. Now okay. So if I go to my Bastion host and if I do, what was I doing? Curl maybe. So when I do a curl to this app instance, and this is our RESTify server basically, we get a hello world response. And I am going to do an Apache benchmarks. This is the same code that's displayed on the slide. So when I do this, it will take a couple of seconds, and it will display me a bunch of results. And one of those results is the request per second. So that's not bad. On a Mac machine with a single CPU, we are getting around 3,000 requests per second for a RESTify application. And if we go back to our slides and, oh, I love it. So let's try to, so if I restart it, I think, yeah, it's now working. So if we go back and do the same thing for our plain HTTP and plain TCP services, we'll get this kind of a response. So, so the plain HTTP is kind of twice as fast. And this is not something that, that's the optimal benchmark, but it shows at least that, if you go bare bones, your responsiveness your throughput will a little increase at least. And it's not surprising that a plain TCP socket application performs the fastest, because you will be getting rid of the entire TCP stack and you'll be communicating at a much lower level at the TCP land. So this creates an immediate question. Is it worth it if we go totally bare bones and write a TCP application or a plain old HTTP application instead of, using a framework maybe? So the answer to that is, as in any profound question, it depends basically. So it's undeniable, the fact is undeniable that if you go bare bones, you'll have an increased throughput, but it will come with a trade-off. First of all, your code will turn into a spaghetti marinara basically, so it will be hard to waddle through and find your way around, and it will be really hard to maintain. And since your code gets more and more complex, and this was just a hello world application. Consider this as an API that has 20 or 30 or 50 endpoints. And as your code gets complex, it will be easy to introduce errors and cause regressions and stuff like that. And also there will be lots of edge cases you have to deal with. And using an API framework normalizes those edge cases most of the time. So, and since your code has gotten complex, it will be hard to use additional tooling and monitoring your stuff and diagnosing your application will be really hard just because of the sheer complexity of your code base. So as I said, it depends, but I can say that 99% of the time, you'll be much better off using an API framework. There is this 1% of the time that you really want to squeeze the latest bit of performance out of your API, or you want to optimize your code so much that you'll need to go bare bones. You can go bare bones in that case, but using an API framework will be good enough to save your day most of the time, I can say. And the next thing is concurrency. And concurrency, as we know, is how many requests are happening concurrently at any given time. Like 100 requests per second, 3,000 requests per second, and stuff like that. And related to concurrency is throughput. Throughput is how much work we do per unit of time. So the throughput versus concurrency in any kind of system, and this doesn't have to be in an API system, but this is typically also observed in API setups, so to speak. It will show this kind of a chart. So we'll first start with a linear increase in throughput versus concurrency. And even this increase might be more than linear, like super linear kind of. And then our slope will be slowly declining. And then we'll reach a saturation point where our throughput will be almost constant no matter how we increase our concurrency. And at this point, if we have infinite resources like infinite CPU, infinite RAM, infinite bandwidth, and stuff like that, then the throughput versus concurrency curve will stay on the same line forever. But it's life, and we don't have infinite resources. So at a certain point, either one or more of our resources will try to deplete, and then our throughput versus concurrency graph will go in a declining stage. And there might be one reason might be the resources being depleted, and another reason for this decline might be you'll have to do additional work per unit of connection. That might be an example. Might be like you create a chat application, and if you do a broadcast message to all your peers when a new person joins into the chat room, then you'll be increasing your broadcast or your load of work that you do when broadcasting linearly per the additional person that's staying on the room concurrently. So no matter what, we'll see this rapid decline eventually, and the goal is to find this sweet spot and limit your concurrency at that point so that your server doesn't start to deteriorate and you'll be able to scale out horizontally the service before it is too late, basically. So that was the throughput versus concurrency thing. And we did our tests with using Apache Bench, as we did before. And although this is good for our demo case, it's not a suitable fit for production. And to benchmark the load characteristics of a production application, you would either want to write your own distributed testing harness by using some of the tools from the left-hand side, or you might want to use an as-a-service solution from the right-hand side to alleviate the burden of creating the setup yourself. And needless to say, these are by no means a conclusive list of those tool sets. There are many other tools around. These are just the ones that I found that have been used the most and that look like the most stable among the gang, basically. And related to concurrency is latency. And latency can be defined by the time it takes for something to come when you stimulate something. So it's the time between a stimulus and a response, and it doesn't have to be IT related. There are latency measures or latency metrics in biology, neurology, and all this stuff. And in our case, it's the time it takes for our client to get a response when it sends a request to the server. And when we plot our mean latency of our RESTful application against the concurrency values, we get this kind of a graph. And if we plot latency and throughput together, we'll see that although throughput relatively remains constant, the latency kind of super linearly increases and goes to unbearable values. So at the level of 20,000 concurrency, we have 10 seconds of latency on the average, which is really bad for your API, and your clients would decide not to use your API if you are at that level of latency. So the matter of fact is it's not the concurrency that matters that much, it's latency that kills. So no matter how high your concurrency values are, if your server's latency is staggering, then you'll have a bad time and nobody will use your API basically. So what have we learned so far? Latency kills. Latency is bad, and it should be the first target that you should be attacking. And you should be also aware of your platform, what your platform is good for and what your platform is not so good for. And we've seen that if we go bare bones, we get a lot of throughput increase, but we compromise a lot of things as well. And most of the time, it's not worth it. But it depends on your implication, basically. And as a corollary, if you add more levels of abstraction to your system, then you will make your API marginally slower. So you should aim to be frugal, and you should think twice when you decide to add another middleware to your harness, basically. And also, I really like abstraction, because abstraction makes your system less error prone. It will be, your system will cause less regressions. It will be easier to unit test different modules because you abstracted them away. However, abstraction also has a cost. If you abstract this a framework too much, then it will be harder to jump through the hoops, and it will be harder to reason about your application or trace your application and stuff like that. And therefore, if you are making more than 3 levels of indirection, you basically go into limbo and get lost forever, which is also known as the inception rule. You should not go more than 3 levels unless you absolutely need to. So that was a summary. Related to this throughput concurrency is the topic of optimization, and you'll have to optimize your stuff, and to optimize your service, you'll have to measure it first, because optimization without measurement is a futile effort, basically. So, this begs the question of what shall we measure in a Node.js setup to be able to optimize our system. And there are a bunch of things that are more important than the rest. First of all, you should always keep an eye on your event loop. The reason is Node.js hates blocking I/O, and anything that blocks the event loop will block the entire API for a long time, which will make not only the endpoint, not only the part of the thing that's blocking event loop not work, but anybody that connects to your server will also not get any response out of your server. And also, Node.js is really sensitive to memory leaks. Therefore, you should monitor your heap utilization very well. Then the reason for that is, since Node applications are long-living, even if there is a small leak in the memory, it will accrue over time, and you will get system out of memory exceptions, and your application will crash eventually. And other things that you can do is to track your internal and external API responses and how long it takes. And you can also keep an eye on the concurrency level, as we said, and because you will need to cap your concurrency at a certain point before it is too late, and then scale out. So enough of the theory, I guess. So let's create something real that we can play with. So we'll have an API that infers what a web page is all about. And for that, we'll have an API endpoint like this. This is a graph API that uses the beta version of Facebook's GraphQL language. But it doesn't. It is the language that we use, or the framework that we use, is not correlated with the things that we are doing. So we should have been creating a RESTful API, and the things that we'll do will be also similar. So this is our API endpoint. We send the API a payload that contains a URL, and then the API does a bunch of natural language processing in the background, kind of creates a textual representation of that URL, and comes up with a set of keywords that are supposedly related to that URL. So this is how the API works, and we won't be diving into the code. In this tutorial, we'll be treating this API as a black box and try to analyze its performance characteristics. And the source code is over there. You can go to GitHub and download the source code and look how it works if you are interested in it. And our initial topology will be relatively simple. We'll start with a single monolithic application that does all the things, that fetches HTML, simplifies, does the conversion, does NLP. And we'll have a bastion host that we connect directly to this API, which will be doing our benchmarks and measurements and stuff like that. And just for the fun of it, let's see if our API is working. So I'll first exit here, and I'll stop my former cluster, and I'll go to, what was that? And those scripts are also in the source code. Let me show you so that you don't have any questions in your mind. So for every part of the tutorial, I have set up start and stop scripts. So for this 0041, the setup cluster just initiates a bunch of Docker images for us. And then we run the start cluster, which runs the node service on our machine. And there is a corresponding stop cluster, which tears down all the applications so that we can start from scratch with a different setup, basically. So let's test our API. So if I send a URL to my API, and this is the URL of the conference, to be able to show that it's not giving you garbage output, it's not hard-coded, it's doing its job supposedly well. So when we send, come on. This works too. So let's try it again. So if I send this address, it does some work in the background, and okay, it's not resolving the URL, so we'll be doing some of the conference offline, I think. But anyways, this is the actual responses that it's supposed to get. So when we send it a URL, it will get a list of tags for us, like performance, responsive, intuitive design, and stuff like that. And we can do the reverse as well. So we can send a set of tags. We can send a URL to the API and get a list of tags. We can give a set of tags to the API, and we can get a list of URLs that the tags is associated with. So that was how it works, basically, which it didn't because, honestly, conference Wi-Fi sucks. So this was the initial topology of our API. So let's try to test the API that is not working end-to-end and see how it performs. I love live coding. It's really exciting. It's like being an adrenaline junkie, I guess. So I go to my Bastion host, Fluent Bastion. So hopefully this will work better because it will be using a static Node.js service I just configured just in case the Wi-Fi would be like this, basically. So let's do an ls. We have two A/B tests in here. So I'll first do this AB000 get tags. This will run this script, like call this get tags endpoint with concurrency level 10, concurrency level 2, and 10 requests. And as we see, we get around two requests per second. So which is nothing at all, basically. The API for the get tags endpoint is really slow. And if we do the same thing with AB001 get URLs, it responds really fast, and it is 2 orders of magnitude faster than this get tags one. So there's something with this get tags API, and we'll need to inspect it further to see what's happening. So if we look at our source code, we have this get tags loop thing, and also this get URLs loop thing. So I'll run this get tags loop.js, and this is all in the source code. You can look how it works. Basically, it's just making back-to-back requests to our get tags API endpoint, so that we can test other stuff, basically. So I'll again clear. I'll again go to my Bastion host. Bastion. Like, the window, like this? Okay, so I'm now on my Bastion host again, and as you see, I am making back-to-back requests to the get tags endpoint. And we have seen that this get URLs endpoint was faster. So if I do a AB001 get URLs, I should get a faster response, which I am not getting. So the response is 2 orders of magnitude slower right now. So it's suspicious. So instead of doing this get tags loop, let's request this get URLs endpoint in a loop. So we have 2 endpoints. One of them is get tags and the other is get URLs. And then run the same benchmark on here. As you see, our performance has raised over 3 orders of magnitude, which means there is something with this, get tags endpoint. It's possibly blocking the event loop, and it's probably consuming a lot of CPU. So to see how the CPU utilization, I'll try to install HTOP if my network works well. If it doesn't, I'll just skip it. Come on. Come on, you can do it. OK, it's not resolving. Anyway, so if we did an HTOP in our system, we could see that the CPU utilization is around 90 to 100%. So not only this get tags endpoint is blocking itself, but it's also consuming a lot of CPU, and it's much likely blocking the event loop. So we have a hypothesis that we suspect that one of our API endpoints is performing badly, and also it's blocking the event loop. So how can we be sure that it's that API code that's the event loop blocker, but it's not something that's running in other place of our application, basically. So to find this, we'll have to do 2 things. First, we'll need to add props to our application by doing some sorts of dynamic tracing. And also, we'll need to create a REPL to access our server remotely. And the REPL thing is really useful, and I also use it in certain production instances. It enables you to remotely access to the runtime of your Node.js process so that you can query what's happening, you can look at global variables and stuff like that. And for the REPL, I will be using Vantage. I have seen that people also use Kang as an option, and you can even roll out your own Node.js REPL by using the REPL API of Node.js if you want to. And if you have written command line Node.js applications, creating a REPL is not that hard. And the text is a little small, but I'll just go over it to explain, basically. So we define a command, and in the action part, we describe how this command should respond to a remote call. So to clarify, this code is running on our Node.js instance, Node.js service, so to speak, which is currently the monolithic application. And we are calling this command remotely from our Bastion host. And by using Vantage, we can do a lot of things with this REPL. We can take a core dump, for instance. We can start profiling and stop profiling and gather profile logs. We can take a heap snapshot. We can even shut down the server. So since you have kind of a root access or kind of a probed access to your server, so to speak, sky is the limit. You can write any kind of logic to inject to your code base. That also has its security implications, but you can secure it. There are ways to secure this, and it's out of the scope of this talk. I'll just skip that one. And for adding props, normally we should have been doing dtrace or xtrace or something similar to that. But when I tried to install dtrace on a Debian Docker container, I bumped into a bug that was not allowing it. So I created this library to scratch my own itch, basically. It emulates dtrace behavior, and it's really lightweight. It can be used in production, but I suggest you not to use it in production, because first of all, it's not battle tested, and secondly, there are better options that can be that fit in a production use case, which we'll see in the following slides. So to use this library, we use the trace function, and we put a bunch of traces on different parts of our source code. And this trace basically sends an event over the network, over the wire, basically. And on our Bastion host, we listen to that event, and we try to chart our outcome by using a graphic charting library and chart it on the console. But you can use any kind of other visualization tool since you have the data, you can visualize it however you like. So let's see how this one works as well. I'll go back to my, where is it? I'll go back to my console. So let's do this get URLs loop again, or let's do get tags one. It will show the performance characteristics better. So if I do get tags in a loop, and I'm again on the Bastion host, and I'll do a Vantage app node is our RESTful node that's living on a different machine. And if I do Vantage app on port 8003, which is our service port as well, I'm connected to my remote machine right now. So I can do help, and I can get a list of commands out there. So I can start instrumentation, stop instrumentation, shut down server, toggle logging. So let's do this toggle logging just for the fun of it. And since I am being bombarded by this getTags API, I am logging all this API and API requests remotely on my Bastion host. So let's toggle logging again so that I can do stuff. And I'll do another help to see what commands are available for me. So one thing that I'd like to show you is this REPL. It's really powerful. This enables me to directly connect into this the remote instance. So I can do like process PID, and I'll get the process ID of my remote instance. And as I said, sky is the limit. I can do global process fluent cache, which is a variable that I have defined globally on the source code, and it will allow me to see the current visualization of the application, or what I have in cache, or what's happening. And I can even call remote methods and execute certain actions from the REPL too. So I'll just exit this REPL. I'll do another help. I'll start instrumenting to show you how the probing thing works. And this is also similar to other dynamic tracing tools. Like if you do dtrace, the process will be more or less similar. So if I do start instrumenting, come on, instrumenting, it will start an instrumentation for me. And where am I? Fluent Bastion. And this is the Keras scripts. As you see, this folder has my tracing scripts, so I'll cd into that. ls. And this sounds tempting, trace all the things. So I'd like to trace all the things. So let's do it. Trace all the things. So we see that our event loop delay is around 1 to 2 seconds. We are utilizing CPU around 90 to 100%. And this request per second is not quite important because we are not testing the maximum requests per second that the application can handle. But the CPU usage and also this event loop delay are really signals that indicate that something is going haywire. And to prove it further, I can stop this one and do this get URLs loop and then see how it behaves. And as you see, the event loop goes to sub-millisecond range, and our CPU utilization has also gone down to less than 10%. So it looks like really our get tags loop is blocking our Node.js event loop basically. And I'll just want to show something else, which is kind of cool. So if I do, let's trace memory usage maybe. Trace memory usage. So you can see a real-time chart of the memory utilization on your console, which I find it cool. But there are other visualization tools that you can use. So this is just to show how cool it is. But it might not have kind of a practical production use maybe. The memory is still high. anyway, so it might be a glitch in the system. But so at least we have we have figured out that something is wrong with our API endpoint. So I'll go back to my slide. And in production, as I have indicated, we can use other tools. One of them is for a Linux environment, you'd prefer to use perf events, and you can do this node -- perf basic perf only functions to get a more understandable real representation of your Node.js performance. And if you do this recording and connect to your server, you'll get this kind of a flame chart. And by using that flame graph, you can find what part of your application is running most on the CPU. You can drill down into different methods and different parts of your API. And what this does is it just statistically samples all your stack traces to come up with this kind of a graph. And it's really useful. You should Google it if you haven't done already. So this is really a powerful tool. And so for this, perf event is one thing that you can use. If you are on a Solaris operating system for some weird reason, you can use dtrace. And there are a bunch of other tools that you can track transaction latency. One of them is a Java-based tool, which is Zipkin. And it is used in the production most of the time. And to track runtime memory utilization, you can either use an as a service solution, or you can install your own by using something called memwatch. And to help you get away with the burden of installing all this infrastructure or monitoring stuff, there is always monitoring as a service solutions that you can use. And there are many around. This is not a conclusive list. It won't be as efficient as using a dtrace or xtrace and coming up with a flame chart of your own. But 90% of the time, using these tools will be both much easier to reason about or to follow, and it will show the root cause of your issue most of the time. So I would suggest you to first start with using a monitoring as a service solution. And if that solution is not sufficient to solve your performance problems, then dive deeper and take a core dump or start tracing your application or stuff like that. Because analyzing a stack trace is really cool, but also it's painful and it might take days or even weeks to figure out the root cause of a problem.